All right, hey class, let's get started on chapter 9. So chapter 9 is pretty cool. It's also a lot more of the same. You can't get away from SN1, SN2, E1, E2 reactions. We're going to be mostly talking about E1, E2 reactions today in terms of alcohol. But before we get to that, let's go ahead and talk about these. You should hopefully know an alcohol is some kind of R group with an OH on it. An ether is an oxygen, between two R groups. And then we have this cool thing called an epoxide, which is essentially you have an R group here, an R group here, and then oxygen joins the two of them together. A little more vocabulary here. We have an enol, which is an alcohol attached to a carbon with a double bond in it, and a phenol. So this whole thing is actually kind of a common organic compound. We just call it phenol, but it's a benzene ring with an alcohol attached to it. All right, we're going to talk about naming here. So when you go to name something with an alcohol, the alcohol actually takes precedence. Now this rule has changed from even when, for example, I was in organic chemistry, but alcohols, they've decided, are so important that they actually win everything. So when you go to label these, normally you would say, you'd look for the longest chain, and that hasn't changed. We do that. And we'd say there's 1, 2, 3, 4, 5, 6 carbons on this thing. So you know it's going to be some kind of like hexane. In the past, we go, in previous chapters when we've gone to name something, we look at the substituents on it and we want the lowest number. Now the alcohol will always get the lowest number. So it kind of takes away the guessing and going back and forth. So if alcohol always gets the lowest number, what I mean by that is this one has to be 1, 2, 3, 4, 5, 6, for example. So if alcohol gets the lowest number, you name the other stuff first. So this would be like a 5-methyl, because we have a methyl on a 5 group. And then you name the next part the hexane, but you don't write the E on it. And the reason for that is now we're going to put where the alcohol is, 3-ol. So it's 5-methyl hexane 3-ol. And that just goes again to show you how important the alcohol is in this methyl hexane that we have here. If you have like a cyclohexane or a cyclo anything, in that case you don't break it apart. You just call the whole thing. So this whole thing would be called, for example, hexanol, and then you want to number the next substituents on it with the lowest number. So you wouldn't want to, for example, go, we have this methyl group here. So once we figure out that we've got the hexanol right here, we wouldn't want to go 1, 2, 3, 4, 5. We still want to go to the lowest number. So 1, 2, 3. And that's why this is a 3-methyl cyclohexanol. Same situation over here. We already know that this is a hexanol, so you can almost like circle it and be like, that whole thing's hexanol. This has to be 1. The next thing is you try to find the lowest number next to that. So we wouldn't go 1, 2, 2, 3, 4, 5. We want to go 1, 2, because this is the closest one. So this was our 2, this is our 5. It's 2, 5, 5. Trimethyl, so hopefully that's not too foreign to us. Cyclohexanol. So overall, it's not too different from our current naming. It's just that the ol takes place, or takes precedent over everything else. All right, so let's go ahead and name these things. We always want to look for the longest chain. 1, 2, 3, 4, 5. I see a 5. Now I would normally call this a pentane, but I know because it's got an alcohol, it's going to be a pentan dash something dash all. All right, we know that this one is our number 1 because again you want to put the lowest number on the alcohol. 1, 2, 3, 4, 5. So we have a 3,3 dimethyl. Again, we want to kind of break it apart. We know it's a 3,3 dimethyl pentan. And then the alcohol was on the 1. So we'd call it dash 1 dash all. Okay. Now we get to this one. Hopefully you recognize right away that we got a cyclohexane with an alcohol in it. So this is going to be some kind of cyclohexanol. In fact, it's kind of nice to write that down because we don't have to break it apart. Personally, I prefer that. The next thing to pay attention to is we have two stereogenic centers. They are both pointed in towards us in the plane, so they're both in the same direction. So this would be a cis situation. And now we just have to figure out which number this methyl group is on. So we got 1, 2. Remember, the alcohol has to have a 1, so this one, the closest thing is a 2. You wouldn't go all the way around to a 5. So 2 methyl cyclohexanol, and that's how we would name that thing. Okay. Then we have ethers. So ethers are kind of interesting. They essentially will break apart into two different portions. So thankfully, we've already been kind of labeling them in terms of nucleophiles. So for example, if we had something like this, we were calling this ethoxide. And when we had, and that would have a negative charge, when we had something with 3, right? We're calling that propyl oxide. And so anytime we have, if we have 3, or we even had the tert butoxide, I don't know if you remember that. So if we had, actually, let me put an oxygen there. I was gonna do something different, but. Okay, so if we had this oxygen with like the cross on here, so we got this, we even called this tert butoxide. So essentially the oxygen is bound to something that's hopefully smaller than the other thing. And in this case, we have the oxygen bound to this ether group. So this whole thing right here would be an ethoxide if it were negatively charged, but we're just going to call it ethoxy. So this group right here is called ethoxy. And then you just look at the group that it's bound to. That should have 1, 2, 3, 4, 5, 6, 7, 8 carbons on it, so that's an octane. And then the rest is the same as usual. Just as long as you know that this is ethoxy or butoxy, or whichever other compound you're going to get, methoxy, if there's only one, for example. So this is an octane. And again, we're just going to do the numbering the same, 1, 2, 3, 4, start on the far end. So this would be 4 ethoxy octane. Okay, then we have epoxies. Yay! These are kind of cool because you name both of the carbons that they're on. So this would be 1, 2 epoxy cyclohexane, because you have the cyclohexane and the epoxy is attached to 1 and 2. Here, the propane takes precedent, so it's kind of hard to see, so you want to be real careful here. The propane actually be something like that, and on your 1, 2, which you'd want to start your numbering, they're not because of the not because it takes precedent, but because of the E comes before an M. So we're back to our normal rules. The only time we broke rules was with the alcohols. So we have 1, 2 epoxy, and then on the 2 we also had the methyl propane. And then of course epoxies can have stereogenic centers, so in this case we'd have a cis situation when the epoxy happens to land on the 2, 3 of this pentane. So the pentane goes like this, and just labeling the smallest way will give us the 2, 3. We wouldn't want to have it flipped around. So yay, it's a naming. All right, now let's get into the fun stuff. Let's do some reactions. All right, so we already have an idea of how to prepare alcohols, and we're going to be talking a lot about alcohols again today, like elimination reactions, etc. So in preparing alcohols, for example, if I gave you this primary bromide, and I said react that with OH minus, hopefully right away you'd be like, huh, I recognize this. This is a strong thing. This is a primary thing that would react via SN2. So we got a strong nucleophile, a good leaving group, a primary carbon here, or a primary halide there, and you'd end up with that. Right? And an SN2 reaction, just to remind you, this would have attacked that carbon, this bromide would have left, and we would have been left with Br negative as well. But the main point is we prepared an alcohol. We just made one. Yay! Can you name it? Let's hope so. Actually, let's go ahead and do it. So you got 2, so it is an ethane 1 all, which common language would just call it ethanol. Okay, then we have something like this. We can prepare an ether too. So for example, if we react it with OCH3, that would attack that. That would go off this way. This is strong, that's a good leaving group. This is primary, SN2 again. And we would get this methoxy ethane. Okay. Now, that we know how to prepare alcohols, which again we spent kind of the last chapter doing, let's break them down. Let's take those suckers apart, okay? You can actually make them into nucleophiles. Like, I don't know if you wondered, if you sat around at night wondering, okay, this is great, but how do we make this OCH3 negative? Well, you make it via pretty much one of 2 reactants. This Na plus H thing is called sodium hydride. Or this amide thing, like this. So one of those 2 will break down an alcohol and make it into an alkoxide. So you can see how it does it. The hydrogen here grabs a hydrogen off of whatever alcohol you have, and then those electrons are free to go back onto the oxygen, and now you have this alkoxide nucleophile, which you can use to make ether or something similar. So you should be familiar with this as a nucleophile. We used it a lot in the last 2 chapters. Okay, so let's see what would happen here. Let's do that. Let's first make the alkoxide nucleophile, and then let's react it with a halogen, an alkyl halide. So in our first step here, we are reacting it with sodium hydride. Yay, my dishwasher's done. Okay, so kind of like we talked about before, this is going to grab that hydrogen, and the electrons from the hydrogen are going to go onto the oxygen. And we now have this beautiful nucleophile that's ready to attack. We also, and it would be negatively charged. Now the sodium can hang out here. In fact, we'll see if we ever do a complete reaction, we'll see that the sodium's kind of chilling with this thing. But now we can react it with our second reactant, which is this. All right, hopefully you remember what happens. This is just a standard SN2 reaction. We have this primary alkyl halide, and we've got this nice nucleophile here. And it's going to come in. It's going to attack there. Those electrons are going to go on there. We have an oxygen now, and now these 2 carbons are going to be attached. So we just made an ether. Our bromide is now off in another world, and our sodium can kind of hang out with it. So you can maybe do NABR if you want to. All right, so hopefully not too scary. Pretty much we just added this step, and this should be a bit of a review. All right, now this is pretty rad. I like this a lot, and it's something to pay attention to. If you ever have an alcohol and a halogen, that's how you're gonna get an epoxy. So hopefully you can see a base comes in, it grabs this hydrogen, making this oxygen by itself, see it right there? It's now negatively charged. And it's like, hey, I can do my own SN2 reaction. And it comes down, it grabs this carbon, and it knocks that halogen out of the way, and you get an epoxy. So we'll do an example here in a little bit to make sure you haven't forgotten that. But the big hint on this is you got an OH and an X on adjacent carbons. All right, let's do a little bit of practice. Okay. So we got this propane 1-ol reacting with sodium hydride. We can generally ignore the sodium, right? We don't usually like it. So you can just think of it like that. And this thing right here would grab the hydrogen, the bond goes onto the oxygen, and you're left with a nice little nucleophile ready to attack. Your products, in case you do want to know them, would be H2 because this thing grabbed the H, and the sodium, which again could be hanging out over here by the negatively charged thing. Okay, we have the sodium amide thing right here. Again, this is these are the two main things that will be used to rip off a hydrogen. These are really good bases. Okay, so in this case, the electrons from the lone pair here will come and snag that hydrogen. Those electrons go on the oxygen. And we've got a really cool looking nucleophile. Additional products would be NH3, because this NH2 grabbed the H, and that sodium, which again would probably be a lot closer to hanging out over here. Okay. So this is how we prepare those nucleophiles. Let's do a two-step reaction where we actually make something. Okay. I'm not going to do each individual step because we're just looking at the overall product. But picture this. This H is originally going to grab this H, and you'll be left with a nucleophile here. This is pretty much no different than how we were doing things before. It's going to attack this carbon because that's where the alcoholide is. So we can pretty much draw the exact same product. So boom, 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 and then down to an oxygen. We got the methyl group right there. And then attached to that oxygen is going to be 1, 2, 3 carbons. So you could even, if it would help you, you could draw this bromine flipped around like that. And then just picture these two things here, or actually just draw out the oxygen here and here joining up. And that's how we got that. Okay. I don't know why they gave you this. Maybe just like a hint in case you couldn't figure it out. I'm gonna cross it out because we can figure this out, you guys. We got this. Okay. I'm looking at this thing and I immediately see something's funky about it. You wanna know what I see is funky? You got an alcohol, you got a bromide on adjacent carbons. You remember what that forms. That forms that cool looking epoxide. Like that. Again, the way it did it is that the hydrogen took this hydrogen. We were left with a negatively charged oxygen. The negatively charged oxygen then attacked this carbon right there and it resulted in this epoxide. Our products we had left would be a sodium, the bromide leaving group, and when this H grabbed the H from here, we would have H2 gas. All right, cool, right? So anyways, I think these reactions are pretty rad, and I think it's more fun that we already know some of the intermediate steps in between there, so we can start building. All right, so OH by itself is a poor leaving group. Like, we couldn't use a nucleophile to come in and attack it and make it leave, but you can make it a good leaving group by attacking it with a strong acid. So essentially, again, you're not going to have an alcohol just take off. You can't attack it with a nucleophile, but you can have an alcohol grab H from a strong acid. When it grabs an H from a strong acid, then you have this water. Water has a positive charge. It kind of wants to take these electrons with it and leave, and it makes it a good leaving group. So again, an alcohol plus strong acid means you have something with a good leaving group. Okay. If you have something with a good leaving group, you can do all sorts of reactions. You can do SN1, SN2, E1, E2, depending on the situation. All right, so there are a few things that we're gonna do. We're mostly gonna focus on elimination today. We'll eventually get into substitution. But these are the main reactions. And again, they're very similar to ones we already discussed. We can take an alcohol and we can do what's called a dehydration reaction. The reason it's called a dehydration reaction is because in order to do an elimination, you're eliminating a hydrogen and an OH. H plus an OH is water. So we just call it dehydration. And then you get this double bond here, much like a regular E1 or E2 reaction. And then you can also do nucleophilic substitution, which we'll talk about more in the next one. Some other random things you'll see. Although you can't use a nucleophile to attack an alcohol and make it disappear, you can use a nucleophile to attack an epoxide. And when you use this nucleophile to attack an epoxide, all it does is the nucleophile will join one end and they'll push that alcohol over here. So hopefully you can see that. I think that's kind of a cool reaction too. Maybe I'm just fond of epoxides. Okay. So dehydration is a beta elimination reaction. It's very similar to what we've already been doing, in which the elements oxygen, hydrogen, and hydrogen are removed from the alpha and beta carbons respectively. So no different than what we're used to. Here we have just some kind of alkane. You react it with H2SO4. Once again, what's going to happen is the alcohol is going to grab the hydrogen, making it a good leaving group. And then the hydrogen can be grabbed by something else, usually the remainder of this, and it will result in a elimination reaction in a double bond. Same thing here. One thing to think about is this para-toluene sulfonic acid. We call it TSOH. I think I've heard some people call it tosyl acid, but we'll just call it TSOH. It is a strong, it doesn't look like it, right? But it is a strong organic reaction. Organic acid, I don't know why I said reaction. Okay. Okay, so let's look at the dehydration of 2-methyl-butanol. I want to show you how similar it is, any dehydration reaction, how similar it is to what we've already done. Okay, so 2-methyl-butanol. Hopefully we know how to draw that already. We want to say it's got a butane group. Okay, on the second carbon, there must be an alcohol. On the second carbon, there must also be a methyl group. Okay, so we want to dehydrate it, meaning we're going to have to react it with a strong acid. So let's say like H2SO4, which H2SO4 from now on, it's a little bit easier to write it like this. The reason for that is to be like, yo, this H is the most important one. Okay. Which order this stuff happens depends on if it's E1 or E2. We'll get to that really soon. But essentially, this is going to be a leaving group and it's going to go. So this one's going to be our alpha, just like in the past. And we have to label a beta. Now you have two beta options. Here and here, these are the same thing. They're both methyl groups. So you can choose a beta here or a beta here. Hopefully you agree this one's more substituted. So this one should be your beta 1 and this one should be your beta 2. So now when you go to draw it, just draw it between the alpha and the beta 1. We can't forget that methyl group there. And this would be our major product. We could also have our minor product, in which it goes between the alpha and the beta 2. And this would be our minor product. Okay, now I say it's your turn to draw the products formed from each alcohol. When it undergoes dehydration with TSOH, remember this is just a strong acid, should be treated just like H2SO4. And it says label the major product when a mixture results. Okay, so let's do it. This would be our alpha, right? And this would be our beta. We really don't have any other choices. It's symmetrical, so the beta is the same on both sides. Okay, and then we'll just have to draw a double bond between the alpha and beta. Hopefully you recognize, yo, this thing is trans, and we know we need also a cis product, and you'd be so right. What am I doing? I just started drawing the whole thing. So I like to go to the double bond usually, and then I like to flip the other thing. So in this case, we had this thing going up. In this case, we'll have this thing going down. So we have 1, 2, 3, 4, 1, 2, 3, 4 carbons down. So these both would be our major products, these two stereoisomers where we have the cis and the trans. And then we don't have any minor products because we only had one beta. All right, let's do this next one. This would be our alpha. Our beta would be right here. There's symmetry, so both of these betas are the same. So this would be my beta 1. I also have a beta 2 down here with this methyl group here. So we could get this. Hopefully you recognize. We could also get, let's see if I can do it, that. So these, here we had the more cis-like product, if you can see, was like this. And here we have more of the trans. These would both be major. Of course, we would also have the minor, where we're between the alpha and the beta 2. Like that. All right. So let's talk about when which one happens. Our E1 dehydration will happen with secondary and tertiary alcohols. So for example, here and here, both of those would have been an E1 dehydration. What that means is, remember that the leaving group has to leave first. So after it grabs the H from the alcohol, or from the strong acid, and it becomes this water and it becomes a good leaving group, it's going to leave. And you're going to have this carbocation. Now, I think this is something that could have been easily missed on the exam, but whenever a leaving group leaves, you have to, on the last couple chapters, I should say, whenever a leaving group leaves, you have to replace it with carbocation because it took its electrons with it. And so that carbon's like, wait, whoa, I only have 3 bonds, so it has to have a positive charge. And that's the whole point of this elimination reaction, is because the whatever's left over from the acid comes back and grabs that H, and it forms a double bond to take care of that carbocation. Otherwise, it would still be positively charged. Okay, so secondary and tertiary alcohols will happen via E1. You should recognize all of these steps from here to here. Leaving group leaves, carbocations there, a base grabs the H, and the H bonds go there. Same exact thing we've already been doing. The only difference is this first step where you react it with a strong acid. When you have an alcohol that's a primary alcohol, that's when you're going to go via E1. It's because it's a lot less hindered. This thing can get in there, and the acid can get close, and this thing right here, mainly the base, can get close and has no problem doing that, all in one fell swoop. So this is going to grab the hydrogen first. It has to become a good leaving group first. Must. So I'll write the OH. Must grab H first. It has to happen first. That looks nothing like the word first. I didn't make it any better though. So it has to grab it first. I got an idea. Boom, boss. Okay, so it has to grab it first, and then it all happens in one fell swoop. This base now grabs the H, the bond can go down here, knocking this leaving group off, and you get a new pi bond. All right, but wait, there's more. Okay, let's take a look at this one. If we are going to draw this reaction, like without looking at the products, we would say, okay, cool. I recognize that this is secondary, so it's gonna go via E1, and you'd want to draw, hopefully, if you're doing what we've been doing the whole time, you'd want to draw a double bond here, but you'd recognize that there's 5 bonds to this carbon, so you'd pretty much have to do it there. But we know that this thing's only monosubstituted, meaning it only has 1 carbon attached to either end of the double bond, and this is not stable. So why would it even want to form? Okay, so what's going to happen instead is our lives are about to change. Okay, let's go ahead and take this thing and talk about what would happen. And then there's an alcohol right there. Okay, we know that the first step, and I don't know what they're reacting it with, H2SO4. Our first step is that this oxygen is going to go ahead and grab the H. Oh, it's going to go in there. Okay. Now we have this funny looking dude with 2 hydrogens on it. Of course, it has a positive charge now. And that makes it a good leaving group. That's good, because this is a 1,2 secondary currently thing. So it's going to go, it's a secondary carbon right here, secondary alcohol, I should say. And so it's going to want to go via E1. And so this is going to want to leave first. So that leaves. Okay. Remember, whenever a leaving group leaves, we have to account for that carbocation. So now we're in this position right here where we have this positively charged thing. Okay. This is not stable though. Remember that we talked about for a carbocation to be stable, it wants tertiary more than secondary, more than primary. Right now it's at secondary and it's not as stable as it could be. So guess what happens, you guys? This methyl group, an entire methyl group, you could choose either one of these, is like, whoa, bro, you look pretty lonely down there. I'll tell you what, let's switch places and then you can be tertiary. And that's literally what it does. It goes over here, the whole group. You actually don't really draw the arrows because it's like, not really arrow pushing, it's not actual movement of electrons, but you can call it a 1, 2, I want to make sure I call it the right name. Alkyl, yeah, just alkyl shift. Because it's moving between 2 carbons. So you can move anything between 2 different carbons, adjacent carbons, and you're going to get now this, and this. Now it's got a new methyl group, and your positive charge is there. So just to give you an idea of where everything is, that's A, B, C. If this was D, D's now there. Cool. And now it's got a positive charge in the tertiary. Now it's stable. Now it makes sense for the reaction to occur. All right, so I'm going to redraw this just so we can see it better. But right now we have a tertiary carbocation. To remind you what we're doing from the start, this leaving group left, we're going to do an E1 reaction. So in an E1 reaction, our HSO4 negative, which is now a base, is going to come in. This is our alpha now, meaning this must be our beta. It's our most substituted thing. You have a hydrogen right there. That thing's going to grab the hydrogen bond's going to go down there, and you're going to get that. Isn't that cool? I think that's kind of cool. Okay, and this would actually be our major product because it's obviously more stable. You could still also get the minor product, where if this was our beta 1, right? You could have put a beta 2 right here or right here, and you would have gotten that. All right, so let's talk about how these hydride shifts happen. You can move hydrogens, or I said hydride because you can move hydrogens or alkyl shifts when you use and move entire carbon groups. All right, so it says show how a 1,2 shift via either hydrogen or alkyl group makes a more stable carbocation from each intermediate. Remember, tertiary is more stable than secondary and primary. So looking at this thing, I know that I want the carbocation to go there. So if you had a hydrogen here, it's just going to shift over there. And this would be a 1,2 hydride. You can draw this exact same thing, except now the positive charge is going to be in the tertiary location. You can do the same thing here. I see right here I have a chance for it to be in a tertiary location. I'm going to choose it. So, and I'm just going to move that there. And this was again a 1,2 hydride shift. The only time you use an alkyl shift is when you have a quaternary carbon. Do you guys see that? I have 1, 2, 3, 4 things on this. So if you have a quaternary carbon, and I should point out the fact that this is now tertiary. This one's now tertiary, and it started off as secondary, and it started off as secondary. Here we're starting off as secondary, but if I went here, this would be quaternary. You know that you can't put a positive charge there because carbon, it has a 0 formal charge when it has 4 bonds. This carbon right now is pretty happy. So what's it gonna do? It's gonna let go of one of these methyl groups and let them come over here. So this is gonna be a 1,2 alkyl shift. An entire carbon group is gonna move over. And now the positive charge can be here, which is again, tertiary. Excuse me. So hopefully that makes some sense. It's always just trying to be more stable. And once it does that, then it can form the E1 or E2 product. Okay, so from the top, let's see if we can do it. It says, let's look at how this happens, or how this happened. Okay, so we know step 1, first of all, I see this as secondary. So it's gonna be via E1, meaning the leaving group has to leave first, right? LG leaves first. All right, so we take this right away. This is gonna grab one of those H's, and then the H electrons are gonna go here. So we're gonna start off with O, with a hydrogen, with another hydrogen. It's got a positive charge on it. Sorry, I didn't mean to draw this business down here. Hope you can ignore it. Okay, so the first step again, the leaving group is gonna leave. So these electrons are gonna go with this water. Now you've got a water. Congratulations, you did the majority part of your dehydration reaction. And we have a carbocation there. Okay, now you should recognize this is not as stable, this is secondary. Could it find a more stable location on an adjacent carbon? Hopefully you say yes, and that stable location is right here. And so that's what it's gonna do. It's gonna go through a 1,2 hydride shift. And you're going to get it. And that stable location you want it to be at, right there. All right, so now it's tertiary. Now it's supercontent. And now this HSO4, remember this thing took an H, so you have HSO4 negative kind of hanging out. Now this HSO4 negative sees these hydrogens, one of them that just shifted over, and it's like, sup, dude? It's gonna grab that. Those electrons can go down there. This is our alpha. This is our beta. I can do better than this though. I see right away when I did this beta, I'm like, oh, this is secondary beta, but this right here is a secondary beta inside a ring, right? So what's more stable, a beta right here or a beta inside the ring? Beta inside the ring is more stable. So we got an alpha, we got a beta 1 here, and we have a beta 2 there. I'll draw them a little better. There we go. So our beta 1 is right there. So it's actually gonna grab this one. It prefers that one. And then those electrons can go down there. Whoop. But you would also still get the one we just did. This would be our major, this would be our minor. Even though they're both tri-substituted, this one's inside the ring. Those ones always get me. All right. I hope that helped. And I hope you're feeling a little bit better. And if you're not, well, watch the video again or crack your books. So have a great week, y'all, and I'll talk to you later. Bye.